What's poppin' YouTube? Code Adventurers, welcome back to the Advent of Code 2023. Chris here, and last night we soared to Lava Island, chasing reflections, avoiding mirrors, and navigating through the soot and ash. We dodged smack moments, found our way through the mirror maze, and conquered day 13 with style. If you missed the mirror dodging action, catch up, because tonight we're diving into day 14, and I've got my coding compass ready for another thrilling adventure. I hope your coding reflections are clear, and you've got your code mirrors polished, because tonight's challenge promises to be a symphony of light and shadows. If you haven't joined the Code Adventurer crew yet, hit the subscribe button, give it a like, and if you're ready for the mirror dance of day 14, ring that bell to stay in the loop with all things Advent of Code. After gracefully maneuvering through the mirrors and reflections of Lava Island, I'm excited to see what illuminating challenges are in day 14. So grab your coding flashlight, clear your coding mirror maze, and let's light up the code for day 14 of Advent of Code 2023. Code Adventures, are you ready to shine a light on another coding puzzle? Let's reflect on our skills and conquer another coding victory. I'm going to try something a little bit different for this one. I'm not going to read through all of day 14, but the day 14, I guess, is parabolic reflection dish. We figured out where all the mirrors were pointing, a massive parabolic reflection dish. The system must be what provides energy. But in short, if you move the rocks, you can focus the dish. So there's rocks there. The platform even has a control panel on the side left, lets you tilt in one of four directions. Okay, so we're going to have to deal with four directions, okay? The rounded rock, so we'll roll when the platform is tilted, while the cube-shaped rocks will stay in place. You note the positions of all of them, all of the empty spaces and rocks, your puzzle input, for example. All right, start by tilting the lever so all of the rocks will slide north as far as they will go. So as you can see here, all of these little rocks that were down here all stacked all the way to the top. You notice that the support beams along the north side of the platform are damaged. To ensure the platform doesn't collapse, you should calculate the total load of the north support beams. Let's look at this one last time. One other note here, if you notice this column here, this pound sign looks like it acts as a stopper because you've got these two here that this particular rock didn't move. The amount of the load caused by a single rounded rock is equal to the number of rows from the rock to the south edge of the platform. So this here all the way down would be a 10. So it's whatever the index is plus 1. Cube-shaped rocks don't contribute to the load. Okay, so this is like what, 10, 20, 30, 40, 50, 18. Yeah. So 136. Tilt the platform so that the rounded rocks all roll north. Afterwards, what is the total load of the north support? There's a context clue earlier in here where it says that it can tilt in all four directions. I'm curious if that's going to be something in the future, but there's a couple different ways we can approach this. So if we take our puzzle input, let's go to the whiteboard. Okay, so let's do this. We'll take a look at this. Let's talk about our approaches. I'm going to talk about how we can kind of like solve this, and then how I think it'll be easier to solve just in kind of perspective. So we know that we need to move this up here and up here. So you end up with this right here. So how do we do that? Well, we could start down here at the bottom, and we could write a function, and we could say that if we see a 0, move it up 1 index, as long as it's not a pound, right? As long as we don't have one of those cube rocks. And we can do that all the way up. But then you get into a section like this where you've got a 0 and a 0, and both need to be moved up. So then you have to somehow decide that when I move this one up, if there's a free space, check the previous one. If that's also a 0, move that up. But you also have to check that previous 0 to see if there's a 0 down here, to see if it needs to move up, which is doable. We're really just talking about sorting. What's another option? My thoughts on this are, if we treat all of these columns as a string or a slice of string, right? We can reduce the problem by chunking it based on the initial inputs. So what do I mean by that? Well, we know that in this example, if we used the pound as a delimiter, we know that we would have an empty for this, an empty for this, and then we would have all of this as a single string or slice of string. And then what we're really dealing with is dot, dot, 0, dot, 0, dot, 0, 0. So we could do one of two things, but really probably we could just count the number of dots and number of zeros, and then we would create a slice of dot and a slice of 0, and we would put it back in. And then we could split it, and then we could stitch it back together, or chunk it and stitch it. But this is kind of difficult to do. I mean, you could do it looking at a column by column perspective, but it's easier to think about in a row by row perspective. But I want to transpose, so to rotate this 90 degrees and think about all of these as rows. And then I can go row by row, chunking apart on the cube or the pound sign here, and treating it as sections of chunks and then stitching it back together. So if we were to look at this example here, so for that example, if we were to transpose it, we have 0, dot, dot, 0, pound, dot, 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 0, dot. And so our first objective is to chunk it apart. So if we chunk it apart, we would end up with a chunk like this, a chunk like this, and a chunk like this. Actually, we would not have a chunk here. And so then we would order these. You would end up with dot, dot, 0, 0. And dot, 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 0. Then we can stitch them back together, and you would end up with dot, dot, 0, 0, pound, dot, 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 0, which is what we want because we want everything shifted until the rock. And then once this is done, we can transpose the entire, or rotate 90 degrees, the entire grid, do all this processing, and then rotate back to calculate our score. I think that will be fine for this. And then our scoring will just be based on the relation to the top vector. And so we transpose it back. So that's how we're going to implement this. This is the route we're going to take. And then so we just, at that point, the scoring is pretty straightforward. It's just looping, starting at the top. And since we know our length, we can just do something that decrements, or we can start at the bottom and go up. Either way, really. But it's going to be an offset of 1. So if we're at index 9 or 0, you know, it'll be 9 plus 1, or times all the zeros we count. All right, so part 1. So first off, let's grab our input. Let's create our test. And we know the value is 136. 136. Okay, cool. So we run this, and we don't get 136. All right. So then we want to, we don't have blocks. We just have input, and that's just a grid. So we can pretty much yeah, because those aren't spaces, right? No, there's no spaces. So we can pass in our grid and we can say those are our lines. And so our grid is that. If we want, we can do our score as that. S is our input. And we're going to just print out we'll go ahead and run this and we'll get our output. All right, cool. So we'll just validate a couple of things. It starts with 0, ends with period, starts with 0, ends with pound, and then pound period for the last one. Pound period. All right, cool. So we've got our grid. Well, we want to rotate, so we want to transpose it first, and then we want to shift it. And so the way I built a helper function for this ahead of time. So we can actually rotate it, and that's going to rotate our grid for us. So if I'm starting to create some helper functions for AOC. So if we and actually we need to treat this as a string now. Yeah, so if we look at our output here, you can see that we shifted and rotated everything. So this, which used to be this, is now shifted here. And so we're going to work on each of these rows, and we're going to do what we talked about, but everything is going to move left. So if we come back to this diagram that we worked on, if we create another text box and we look at it like this, well, these have extra spaces in it now, but this is essentially what we're going to be working on. The pretty printing that I did has some extra spaces in it. But this is essentially what we're going to be working on. And so we're going to be working from each of these rows from left to right. So the zeros are going to get stacked here and here. And we're going to do that with a sort function. The rocks don't move. The empty spaces aren't really a thing. Same thing with this one, 0, 0, 0 as an example. So we're going to shift everything that way, and then we'll transpose it back, and then we'll do our score. And as you can see, we're looking at this particular view here, but that lines up with what we have over here. The next thing we want to do is we want to chunk these apart. And so I'm going to iterate through for I row in range of G. So now we're working with each row. I'm going to chunk this apart. And so, like I talked about doing, we're going to split on the pound sign. This is simply going to be so I'm going to chunk it apart. I created this chunk function, just part of AOC. In my common library, and what it does is it takes in a delimiter on a slice of string, and then it chunks it apart. This should be helpful in the future, but that's pretty much all it does. So we got back our chunks, and then for each chunk, we want to sort it. Slices.sort, and we're going to do that for each chunk. does it in place. And then G sub I equals 2. We're going to keep this print in, and then we're going to print afterwards. Common dot stitch, and we're going to stitch together our chunks, and we're going to stitch them like that. All right, let's run our test and see what we get. Okay. All right, perfect. So if you notice here, we've got the 2 pound signs on the end, which is expected. And those all get, the zeros all get shifted to the right, which is what we want. This one has 3 zeros. We want that shifted to the right. This one has a cube, so we want these 2 shifted, which again is what we did. And then we have a cube here, but only 1 0 that goes all the way to the right. This one comes all the way over. And then, was that the third line up? Yeah, 0 shifts over to its block, 0 here, and then these 2 shift up. All right, so that all looks right visually. So now we got a score, and we could do 2 things. We could just score it in the position it's in right now. But again, I think I'm gonna guess that we might have to deal with rotating anyway. So for this particular part, it's not that computationally difficult. What we're gonna do is we're just gonna rotate it 3 more times. So we're already facing east technically, and so southwest and then north. So and then we can pretty print that one last time. Let's just check our results. So this should match our expectation here. Just spot checking a couple. Looks pretty good. All right, so now the last thing we need to do is just a score function. So now we want to score this. We're going to take in a grid, which I've set up a grid object, which is really just a string. I can talk more about that later. If you guys want, comment down below. I can do a separate video specifically on it. And so we want to count all of the zeros. So we can just say for row and range of grid, and then we can say for val in range of row, if row, or if val, really I should do v equals to, those zeros or O's? Those are O's. The age-old question. All right. So it will be our score plus equal 1 times our multiplier. So our multiplier is going to be the length of G, which is all of the rows, plus 1. And I guess we could just put I in here, and then we'll do multiplier minus I. So on the first one, we want so we have 10, so it'll be 10 because the I is 0, and then on the next one it'll be 9, and then 8, and then 7, then 6, then 5, then 4, then 3. This needs to be equal to that, and then this will be that score 0, and then we return score. And then we simply score on G on our grid. All right, let's see if that works. 136 versus 154. Okay. So the first question is this, I didn't really validate this output entirely. Let's take a look and see. Maybe I got something wrong. So I'm just going to paste this here. Zero pound 0 pound 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 0 pound 0 0 0 0 0 pound pound 0 0 0 pound pound 0 0 0 pound 0. Okay, so that all looks right. So this looks fine. I don't think that's my issue. So it's definitely my scoring then. So oh, I think this is the problem. It's the length of G, not because that's the index, and we're going to decrement it each time. Okay. Okay, perfect. So now we should just be able to run I forgot to put the test input in. All right. Okay. See if that works. There we go. Awesome. On to part 2. The reflector dish deforms. Fortunately, a button on the side of the control panel labeled spin cycle attempts to do just that. Move the rocks off the edges. Each cycle tilts the platform 4 times so that the rounded rocks roll north, west, south, and east. After each tilt, the rounded rocks roll as far as they can before the platform tilts in the next direction. After 1 cycle, the platform will have finished rolling the rounded rocks in those 4 directions in that order. Here's what happens in the example above after each of the first few cycles. The process should work if you leave it running long enough, but you're still worried about the north support beams. To make sure they'll survive for a while, you need to calculate the total load on the north support beam after, that's a lot of cycles. In the above example, after that many cycles, the total load on the north support beam is 64. I'm a little perplexed. What I don't understand is, are we just getting the final score? Calculate the total load on the north support beam after that many cycles, or each time we get to north. Because this number seems pretty low at just 64. When our input, our initial test, yeah, I think it's just the final, right? It's not the aggregate. Because we were at 136 initially. Okay, so let's okay. We needed to make one modification here. Because we have the rotate, it's just we're going northwest southeast, so not exactly the way that I'd want to go, but we can accomplish it by rotating, because we're technically at north, and then we rotate once. So if we're at north and we need to go to west, we'd have to rotate 3 times technically. So let's go for this first cycle. The total load on the north support beam is 64. Run the spin cycle. It says after 1 billion cycles. That's 1 billion, right? Thousands, 100,000, million, billion. I think, yeah, that's billion. So I think this is another like cycle problem. I mean, it's so I'm running a spin cycle. So eventually we're going to get into a cadence, and wherever that cadence is, we can skip forward in the patterns, I think. But I mean, once we get into that cadence, I guess we can get in that cadence and the score might be 64 after a certain period of time. All right, let's talk about this. So northwest, south, and east. So we can kind of treat that as like our whatever. So if we pretend that we're in north, so this is technically west, and then northeast, south. It's a lot of extra operations, especially for 1 billion, but I don't think we're going to be going that far. I think we're going to end up caching our patterns. Each rotation is 3, right? Because if you're out south, and if we're going clockwise, it would be southwest, northeast, that's 3. And so, yeah, if I do something in here and we call it like cycles, and it's an int, just bear with me. But we always start at north, so we're always going to process. We're always gonna flow north, and then we need to create a function called slide here, because I don't want this in the main anymore. Okay, so that's in there, and then we will move this and we'll say g equals slide g. And then if we run this, int, and we'll call it cycles 0. And this can be test.cycles. Okay. We'll figure this part out in a second. Yeah. Okay, so that works as far as functionalizing that piece. So now we need to ask ourselves, how do we want to do this cycle? So we know that from any location we can rotate 3 times. So we know we need to do the first rotate, and then we can, this could be our cycle. So it's going to be, we're always going to end up oriented north. So it's going to be for range of so we're just gonna make that our thing, and then we're always going to slide kind of bad practice here, but what I'm gonna do is this. I'm gonna say if cycles, this will allow our original to be preserved. We're gonna do this equals 0. Yeah, so we're just going to range over those. And we're going to slide, and then we're going to rotate. Actually, I'm going to remove this. I don't actually need it. So I'm going to do for I equals 0, I is less than cycles I plus plus. Yeah. So we know we always, when we finish, we're going to finish on, okay, so we're north, we rotate to south, west actually, sorry. We slide, we rotate to south, we slide, we rotate to east, we slide, we rotate, and then we're back north again. So we're always north when we get in here. So what that means is I don't need this actually, because this will only go if we have cycles greater than 0. So if I run this again, we never slid. Well, if cycles equal 0, we'll slide once. Otherwise, yeah, I'm not going to put that in else. Okay. So now we can try it. I really doubt it's going to work in its current form. Okay, we need something much smaller to test. So what's the test if we run it after one cycle? Okay, let's see. Let's see here. After one cycle, it's supposed to look like this. Does that match? Get rid of that. Should all be comments. No, we're way off. We are way off. So why? So clockwise is northeast, southwest. If I'm north currently, even though I've already oriented myself to the right, if I'm north currently, then we get to south. All right, let's look at this for a second. Let's label these. So yeah, let's do it there. Okay, so that's correct. Okay, but we don't need to rotate it north because we end east, right? Is that the difference here? So this isn't technically north. This should be east right now. Yeah, so this orientation is, let me put that in here. This might help. All right, north is good. North is what I expect. So west, if I'm thinking about the orientation here, and if we're facing this way, if we were to shift this left or west, I'd expect this pattern to be on this side, so that we should have a hash in the middle. And I don't. It's transposed almost like it's east. So do I just have the rotations wrong? Is it only one rotation instead of 3? We do want to rotate it back to north just for the final scoring, right? Like, we're not going to do the slide north because east... Oh, east should look... I think I have my west and east inverse because we want everything is always sliding to the right. So I think this is correct. Okay, let's validate this though. It's not right. It's still not right. No, that doesn't make sense. It doesn't make sense. Okay, wait, hold on. Is this right? This is right. Yep. Yep, yep, yep. 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 Yeah. Okay. I think we got that. So was it 87 after 1? What's 2 look like? Let's make sure we got this right first. Oh, 69. Let's just do a let's do 100. Let's see what we get. $68. What was our 64? Let's do 1,000. Let's get rid of some of these prints because that's gonna take a while. Interesting. Okay, so at some level of scale, as I was saying earlier, okay, that's interesting. Was it 1,000 that I got? I was right. Yeah. Okay. So let's do this. Let's create a cache and let's cache these somehow. So what we want to do is we want to find how often we get into a particular state. So I've got this pretty method. So can I like and can I chord like So that's the cycle. So I'm wondering if, let's just see. Panic 2. That's the value, but let's do this instead. And we'll do C comma I. And then we'll just panic cycle found 2 and 9. So 2 is the first time it was seen. 9 is the second time it was seen. Is this only on, I guess I have this other one here, but that's only 2 cycles, so that shouldn't be a problem. So then if we see this between 2 and 9, that means that our test input should encounter this, what, every 7 or so? I can skip I ahead, right? So then, yeah, so if our cycles go to cycles or let's say cycles divided by I minus C. So if we've got 1 billion, let's say, and okay, so I equals to I plus, so we want to be at I, and we want to add to it the cycles. Well, we want to add enough cycles. How do we know how many cycles to add? So we can figure out how many times. So isn't it like 6? Our cycles are what? Our cycles are 1 billion. I don't have them in here yet. It's 1 billion divided by 7, right, in this case, which gives us this number. But we know that there's a remainder, so we don't care about the remainder. So really we just need the module of it, right? So I minus C, which is 7. So the module of that this is what needs to happen. But is it cycles? We went through 7 cycles, right? This is our max number of cycles. So it's divided by 7, but what I'm trying to figure out is how the first offset of 2 comes into play here. So I think that's true, but I think it's plus I is what we need. And so we only want to skip forward the first one. So let's change this to the actual number real quick. We're getting close, getting close. So I think what's happening is it's finding the other use cases and trying to cycle forward. All right, let's try this again. Whoops. It just came back and I launched it again. Yips. Now I did add this cycle found to true, and so it shouldn't enter this block anymore, and it should just process from that point forward. I think my module here is wrong. It should be cycle minus the remainder plus I. Yeah, because it should be jumping to, yeah, it shouldn't just be jumping to 15. It should be jumping way ahead. Yeah, that's too far in the future. Okay, so we're getting close. That's 7. So what I'm trying to do here is jump forward and then just reprocess the last couple of cycles. And we know if we're in a cycle, we know how far we can jump forward. So we can take our total number of cycles and we can know that the current configuration that we're in, since we know that there's a cycle here, is going to be in that cycle moving forward. And so we then just jump to that, and then we process the few extra records out towards the end. If we can actually run this in the terminal, we might actually see some better output. Or not. Okay, let's see if we got the actual solve. That's it. Awesome. All right, day part 2 finished. So let's look at this real quick, and I just want to highlight. Well, let me get rid of some of this grid printing real quick. There's a couple things I want to highlight here, and then I'll talk about the cycles a little bit further. This is what I wanted to highlight, is that we found our cycle. The start of our cycle was 80 in, and then we found it at 131 again. So that's the second iteration. So we used some maths to jump all the way to the 999,971 because we knew we were in this cycle. We knew that our current configuration was there. And then we just processed the remainder. I don't know, what is this? 1, 2, 3, 1, 2, 3, 1, 2, 3. The remaining 29 records. So in total, we processed maybe 100 configurations. So let's talk about the cycle real quick. I think it's important for us to just kind of go over that again. So the reason why this caching works, and what I ended up doing was just caching the entire grid. So I took the entirety of like this string here, and then I just concatenated everything into a very long string as the key. Not a super efficient key, but it worked. So let's go down over here and let's talk about the cycling. So the reason we can do this performantly is because we know that it is very likely that if we get to a certain configuration, so let's say our configuration is something like, you know, dot, stone, circle, 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 dot, cube or stone, dot, circle. Something like this. We know that every time we reorient it and we flip it and we flip it and we flip it, we're going to get a different set of inputs. But there's only so many different ways the rocks can fall. And so at some point, at some nth position in the future, we're going to look like this again. So in our case, if we go back to our actual problem, that was after the first time we saw a iteration that was similar was 80. So, and then 131 again. So the first time we got into a configuration, this is why it's important to look for the second one. The first time was 80 that we saw this, let's just say hypothetically, this configuration. And then we did not, if we would have just based it on that, well, 80's not right, because the initial start of the board, you're going to have some sort of randomness of the rocks. But eventually by shifting it in these different ways, you're going to end up back oriented. So at some nth position in the future, right, which in our case was 131, at 131, we saw this pattern and relationship between our start and our end. Okay. So instead of going to a billion, which we could do, but as you saw, it took a really long time, we can take advantage of this and know that every 131 minus 80, so every 51 cycles, we're back to the same beginning. Now, we could have just said, let's loop, we could have said loop plus 51 until, you know, 1 bill is reached. Or within 51 numbers of 1 billion. And so that's kind of the kicker, is that we have an offset of 80. We have to loop 51 until we get within 51, and then you kind of finish the rest off. And I guess we could have maybe just cached the configuration and knew what the final configuration was. That'd probably be a better way to do it. But the way that I was thinking is, well, if we know if we know that we can jump by 51, let's get all the way to whatever that billionth number was. So in our case, that number was 999999971. So that was within our 51, right? That's as high as we could go without overflowing the number. And so then all I said was, hey, from this point forward, let's step forward at the current configuration we are at. So again, kind of going back to our drawing, at our current configuration here, we're just going to start there at 9971, and we're going to step forward until we hit our number. And so that's why we only wanted to do this once, and that's why we use the caching here, and that's why I put in this kind of cycle found false true, so that only the first time we found the cycle would we walk through it. And then for the caching, you know, it's kind of a long key, but I just went ahead and utilized this pretty functionality, which just puts every line with some spaces so it's easier to read, which is what you see below in the output here. And then I just said strip the hard returns, and I could have stripped the spaces, I guess, too, but whatever. So that's pretty much the solution. That's how we solve the problem, and that's the logic and the reasoning behind it. You know, I think recognizing cycles like this is important for our development as a software engineer. If we can realize that there are shortcuts to computations, it will help us as developers, because then we can look for those shortcuts. In this case, we didn't have to calculate all the rotations. We could just know the configuration at the end of the cycle and go from there. So, all right, well, that's all I have for today. Hopefully you'll join us next time. As always, over and out.